Never wear a jacket.
You never wear a jacket.
I always do.
Oh, that's true. You do. It's cold. All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Tired. Tired? Doing okay? Yeah, it's end of the semester. It's cold. Why I have a jacket on.
It's the 80 next week.
Okay, good. Because that's my wedding is next week, so I hope it's sunny. I hope it's nice. Okay. So it's the end of week 15. So after today, we only have 2 more lectures left. So my plan for today is we're going to finish up just the last bits of stuff with constraint optimization. And so we have 1 more example to do with the penalty parameter. And so we're going to do that. We're going to start with that. And then we're going to go over 1 last method that you may find useful for your final project, which is variable transformations. Okay. And we're gonna do an example with that as well. Okay. All right. And then after that, I have 1 more set of lecture notes that I'm going to cover. We're going to start it today, and I think we'll probably do it just a little bit more on Tuesday. And the last set of lecture notes has to do with more kind of practical stuff with optimization. So more, after today, that kind of concludes kind of the main content of the class in terms of the theory and the algorithms. But actually applying optimization in practice has a lot of difficulties, and some of you are experiencing that right now with the final project. And so my final set of lecture notes is basically just a bunch of just somewhat random topics that don't really fit together, but don't fit together with some of the other topics we covered in the class, but are nonetheless kind of very important to talk about when you're applying optimization to kind of more practical problems. Okay. Included in that set of lecture notes is how to use some built-in optimization algorithms that MATLAB has made for you. Okay. So actually, a lot of the algorithms that we've covered in the class, MATLAB has some built-in functions for you to call. And so, we'll talk a little bit about how to use those methods probably on Tuesday. Okay. And then, like I mentioned last week, or like I mentioned on Tuesday, the plan for next Thursday is I'm not going to lecture on anything next Thursday. It's just going to be kind of an extended office hours. And so if you're, if you're having trouble with the final project, you want me to look at your code, next Thursday's lecture will be kind of a good time to do that. Okay. And that'll be kind of our last lecture. So, I know quite a few of you have already kind of started with the code. I've had conversations with you, throughout the week. But if you haven't started on your final project yet, I would definitely recommend doing it before next Thursday, so that you can come to the class with questions, and code for me to debug. So that's kind of the plan for that. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. So let's go and pick up where we left off on Tuesday. Okay. So let me scroll up here for just a second. And so this is kind of what we ended with on Tuesday. So, I'm not going to spend too much time on this, but I did want to recap it because our example kind of goes through this method. Okay. Okay. And so we spent the majority of the time last on Tuesday talking about this idea of the penalty method or penalty function. Okay. And so when you have a constrained optimization, you have these equations, either inequality constraints or equality constraints, that you need to ultimately satisfy in your final solution. Okay. And so one approach that we talked about is taking these constraints and incorporating them directly into your objective function with a penalty parameter. Okay. And so if you tune that penalty parameter well, you can get your result to match pretty well with the constraints. Okay. The difficulty is, how do we choose this penalty parameter, and how do we go about, making sure that it's at an appropriate value? Okay, because the optimal value or the best value for the penalty parameter is as small as it needs to be, but while still making sure your final solution satisfies the constraints. Okay, and that can be difficult to do. And in fact, sometimes for just a practical problem, finding the best penalty parameter is really impossible. Okay. And so to help with this, we talked about, sequentially varying this penalty parameter such that, you eventually kind of converge on the best penalty parameter that will satisfy all the constraints and be as small as possible to not have undue influence on the objective function. Okay. Okay. And so the algorithm that we talked about has to do with this. Okay. And so step one of this algorithm, we're going to start with our initial guess. Okay, so this is our initial guess for the design variables, and we call this x naught vector, right? And we're also going to start with an initial value for the penalty parameter, and we're going to start it pretty low, right? And so a good value, starting value for this would be 0.1, even 1.0 is okay too. So you're going to start with a low value of penalty parameter. Okay. Okay, from there you're going to solve an unconstrained optimization using the original function, using the original objective function plus the penalty terms, okay? And so you're going to have a combined objective function that kind of looks like the following here, okay? And then this is going to give you an optimum. So that's going to give you some optimal value, we'll call it xk star, okay? Step 3 is to check whether this optimum here, xk star, satisfies all the constraints, right? If it does, then that's great. And so we don't have to worry about this anymore, and we can terminate our algorithm, and we can just leave it at that. Okay. But more than likely, because you started with a small value of the penalty parameter, right? You're going to need to increase this. Otherwise, the solution is not going to satisfy the constraints, right? And so you're going to take your penalty parameter, you're going to increase it by a factor of c, okay? And so you're going to take c and multiply it by your original penalty parameter, okay? So that's going to increase its value, and then you're going to return to step 2. So you're going to rerun your optimization, but with an increased value of the penalty parameter, okay? And the key step here is that your starting point for the next optimization or the next step is going to be the optimal point from the previous step, okay? And so remember, in step 2, you solved an optimization problem, you got an optimum, okay? And so your next optimization problem is going to start from there, okay? Okay, and so the idea is that you kind of run this over and over and over again, and that eventually you're going to get closer and closer and closer to the constraints, and eventually you're going to reach a point where all the constraints are satisfied. Okay. Okay, so let's do an example to kind of illustrate how this works. Okay, and I have a code that accompanies this that we're going to take a look at as well. Okay, so in this example, we're going to minimize. Okay, so let's minimize the following functions. We have f of x1, x2, okay, is equal to x1 squared plus x2 squared minus 4x1 minus 4x2 plus 8. Okay. All right, and we have one inequality constraint here. And so our inequality constraint is going to be x1 plus 2x2 minus 4. This must be less than or equal to 0. Okay. Okay. And then we're going to start our optimization from a certain starting point, and we're going to start from 0, 0. So x1 is equal to 0, x2 equal to 0. Okay. Okay. So this is our problem here. So we have a relatively simple 2D problem with a single constraint, okay, and an inequality constraint. So that helps us out a little bit. Okay. So just like we normally do, let's compute optimal values for x1 and x2. That satisfy the constraint. All right, so pretty standard optimization here, but we're going to use the exterior method for exterior penalty method. So to use a penalty function method, first thing we're going to need to do is we're going to need to set up our augmented objective function, right? So remember, our augmented objective function is going to be our normal objective function, but we're going to take our constraint and add it in as well, okay? Okay. So our augmented objective function, let's call it big F, okay? Big F of x1 and x2, okay? This is going to be equal to x1 squared plus x2 squared minus 4x1 minus 4x2 plus 8, okay? Of course, this right here, this is our original objective function. Okay. To this, we're going to add a penalty term, okay? Okay, we only have one constraint here, and so we are going to do it like this, okay? So we're going to have RK multiplied by max, okay? Remember, when we have an inequality constraint, we have to use our max function. So you have 0, comma, x1 plus x2, 2x2 minus 4, okay? And that quantity is squared, right? Remember, the square has to go outside of the max term, okay? And so this right here is our penalty term. Okay, for our one constraint. And this RK here is our penalty parameter. Okay. All right, so that's our augmented objective function. So that's the one we're going to optimize in this case. Okay. All right, so the way that we're going to solve this is that we're going to basically use an unconstrained method. We're going to optimize the above function. And I think in the example that I did, I use coordinate search. Okay. All right, so I'm going to show you the code for that in a second. Okay, but of course the key to this whole operation is how we're going to treat the penalty parameter. Okay, so we're going to start the penalty parameter. Okay, we're going to start it at a low value, so we're going to start it at 0.1. Okay. And then we're going to steadily increase this over successive iterations until our result satisfies our constraint. Okay. So the code for this one is C underscore NLP underscore example underscore 5 underscore penalty function. Yeah. Okay. That's just the name of the file of the that's posted on Canvas right now, so you can take a look. Okay. All right. Any questions on this before we jump into the code? Okay. All right. So let's go ahead and jump in the code and see what this looks like. Okay. That's the next example. We're going to do this one first. Okay. Yes. Okay. Yes. Okay. All right. So this is our code here. Okay. And so so in this code right here, this is basically going to be coordinate search with a penalty term, but we're going to steadily increase the penalty term, until all our constraints are satisfied. Okay. Okay. So first we have some kind of initial stuff here. So we have to set our initial point. Okay. And so the initial point, strictly speaking, the initial point doesn't have to satisfy the constraint. So you just need somewhere to start with. Okay. And so our initial point in this case is 0, 0. Okay. We're going to evaluate the objective function here. Notice how I'm using an inline function here. And so, the objective function is down here. Okay. OBJ function. Right. Right. And so in this case, this is actually without the penalty parameter as well. And so this is just the original objective function. Okay. You don't have to do that. You can actually incorporate the penalty term if you want. Okay. And so then we have our convergence threshold as well as S naught. So this is our step length. Okay. So these are all parameters for coordinate search here. Okay. Next thing we have here is are the penalty parameters. Okay. And so you can see here, we're starting our penalty parameter at 0.1, and we're going to grow it at a rate of 2. Okay, so each time we fail to satisfy the constraints, we're going to double the penalty parameter, and we're going to keep doing this until we reach a point where they're all satisfied. Okay. All right, so let's go ahead and start the optimization. Okay, so whenever you're doing an exterior penalty method, you're doing multiple successive optimizations over and over again. Okay. Okay. And so when you do that, you need to have a nested for loop. So you can see here we have a loop within a loop. Okay. And so this outer loop right here, so this for counter is equal to 1 to 50, this is the exterior penalty function part. Okay. And so what this is telling us, since this is the outer loop right here, okay, this defines how many times we can increase the penalty parameter. Okay. And so I set a cap of 50. We're not going to get to 50, but it can double the penalty parameter up to 50 times, which is actually quite a lot. Okay. All right. So next I have a print statement, and so this print statement here just prints out just what the current penalty parameter is. Okay. And then from there, I compute the objective function. So the objective function is just whatever it was before, plus our penalty term here. So we have RK, our penalty parameter, multiplied by max, 0. And right here, I have the constraint. Okay. So you can see here, I've defined a second function here for the constraint, which is pretty simple, actually. So this constraint 1 function here takes in x1 and x2, and it returns the value of the constraint, which is x1 plus 2x2 minus 4. Right. And so in order for this to be satisfied, this has to be less than 0. Okay, that's what our constraint says. Okay. And so from there, we enter our inner loop. And so our inner loop here, this is our coordinate search. Right. So this is pretty standard coordinate search, and so I'm not going to go into this. And so the main things here is that you have to determine the step size. So we have to do it twice. So we have to step in the x1 direction and then the x2 direction. Okay. This should be x2. Okay. All right. And then we repeat that, and then we end up with an optimal value, right? And so at this point in the code, okay, we have an optimal solution. Okay, but we are not sure if it satisfies the constraints. Okay. Right. We hope that it does because we've incorporated the constraints into the objective function through the penalty term, but we haven't done that just yet. Okay. Okay, and so at this point we're going to check. Okay, so this statement here checks to see if we have satisfied the constraints. Okay. And so if we've satisfied this constraints, then this is going to be less than 0. If it is, then we break, right? And so all break does is that it breaks out of the current loop, right? Because if we've already satisfied the constraints, there's no need to iterate any further, so we can just kind of break out, okay? And then that ends that. Okay. And then at the end here, we print just what the optimal design point is. And so that's x1 best, x2 best. Okay. So let's go ahead and run the code. And so this code here is, we basically copy and pasted coordinate search here. We've had to make some modifications to include the penalty term, but that's essentially what it is. Okay, so let's go ahead and run the code. And let's see what we get. Okay, so you can see here that we had to run it for 13 iterations, right? And so we start with a penalty parameter of 0.1. With the penalty parameter of 0.1, the constraints were not satisfied. Okay, then we move up to 0.2, okay, then 0.4, 0.8. Okay, it took us all the way up until our penalty parameter got up to 409.6 until we satisfied all the constraints. Okay, and at this point, the optimal design point is 1.61, 1.615 for x1, and our value for x2 is about 1.2. Okay. All right. And so if you were to run this problem without this sequential, exterior method, it would probably take you a long time until you were able to find a solution that satisfied the constraints. Okay. All right. Any questions on this? Okay. Yeah, 409 is actually quite a lot. So this is actually quite a large penalty parameter. Sometimes it takes that much to find an optimal result. Okay. All right. Okay, so let me go ahead and stop this. Let's bring back the iPad. Okay. So let's go over one more technique for dealing with constrained optimizations. Okay, so let's talk about variable transformations. All right, so for the last few lecture sessions, we've been going over methods for constrained optimizations, okay? And and primarily we've only been going over one method, which is the penalty function method, okay? The penalty function method is okay, it works. You're going to use it for your final project, but there's no guarantee that that when you use the penalty function method that your result is going to be satisfy all the constraints. Okay. It turns out there are certain other techniques that you can do, relatively simple things, and so that's kind of my theme here, to make sure that you satisfy certain types of constraints. Okay. And one of those things that you can do is to simply transform the variables from one form to another. Okay. This can be useful for certain types of constraints that are very common to see in a lot of optimization problems. Okay. Okay. So I'm going to list two here that are probably the most common and apply to almost every engineering optimization problem out there. Okay. So the first constraint here that's very common is our design variables are only able to take positive values. So they must be non-negative. So that's a pretty common one. Mostly just because, the design variables in our optimization problems often represent some kind of physical quantity, either a physical length or some kind of material property. And it's very rare for these to be able to take negative values. Okay. So almost always you're going to be working with non-negative design variables. Okay. The second most common constraint that you're going to see is you're going to see design variables that are constrained by an upper bound value and a lower bound value. So that second one applies to your final project, right? So every design variable that I gave you for the final project has an upper and a lower bound, to them. Okay. And that's mostly just due to kind of, a lot of times due to physical considerations, physical constraints. If you're designing like the dimensions of a structure, the structure can only be so large. And sometimes these are just kind of constrained due to budgets as well. Okay. Okay, so all these constraints here can be dealt with in using penalty parameters, but it can be a little bit cumbersome. Okay. Especially the upper and lower bounds, because technically the upper bound constraint and the lower bound constraint are separate constraints. And so for every design variable, if you have an upper and lower bound, that's going to contribute two constraints, right? And when you have a very highly dimensional problem, and so let's say that you're looking at the big truss problem, where you have 10 design variables, or each design variable has an upper and lower bound, just the upper and lower bounds are going to contribute 20 constraints. Which is a lot, which is pretty annoying to deal with, right? Not hard per se, not difficult, just very annoying to kind of type out and read a code from that. Okay. Okay, but there is a better way to deal with these. Okay? And so if we transform our original design variables into other ones and incorporate that into our objective function, then we can automatically satisfy these constraints. Okay. And of course, this has the caveat of only working when your design variables show up explicitly in your objective function. So this is not something that can be used for your final project, unfortunately. Now I think about it, because our objective function there doesn't have our design variables explicitly. Okay, but it can work for some other cases. So let's go over two variable transformations. Okay, one for the first one and one for the second one. Okay, so for strictly non-negative design variables, okay, we have three options that we can take here. Okay. Okay, so the first being xi is equal to absolute value of yi, okay, or we have xi is equal to yi squared, okay, or xi is equal to e to the yi, okay. Okay, and so in all these equations here, the xi represent your original design variables, okay? And then what you're going to do for the variable transformation is plug in the yi's instead, okay? Okay. All right, so for example, let's take our previous objective function, right? And so if we have f of x1, x2, okay, this is equal to x1 squared plus x2 squared minus 4x1 minus 4x2 plus 8, okay? And we have the constraint that x1 and x2 are strictly non-negative, and so they have to be greater than or equal to 0. Okay. Instead of solving this with the penalty function method, what we can do is we can just plug in for the x's instead, okay? We're going to say x1 is equal to, and I'm going to use this middle one here, so I'm just going to plug in y squared, okay? x1 is equal to y1 squared, and x2 is equal to y2 squared, okay? So everywhere we see x1, x2 in our original objective function, we're going to plug in those expressions there, okay? All right, so now our objective function is going to be f of y1, y2, okay, this is equal to x1 squared, so we have y1 squared squared, so that's going to be y1 to the 4th power, okay, plus x2 squared, and so we're going to plug in y2 squared for x2. We have y2 squared squared, and so that's going to be y2 to the 4th, okay, minus 4x1, this will be 4y1 squared minus 4y2 squared plus 8. Okay. All right. So now we're gonna optimize this function for y1 and y2. Okay. And then once we obtain the optimal values for y1, y2, we're going to use our transformations to get back the x values. Okay. And so whatever we get for y1 optimum, we call it y1 star, y2 star, okay? And x1 optimal value, so x1 star is equal to y1 star squared, and x2 star is equal to y2 star squared, okay? So that's a kind of a simple transformation that you can do when you have the constraint that the variables must be non-negative. Okay. All right. Any questions on this? Okay. All right. So that's the transformation for a non-negative design variable. All right. So the next transformation we're going to do is for an upper and lower bound. Okay. So this is quite common. And so in this cases, we have our xi, and the xi is bound by a lower bound on the left and upper bound on the right. Okay. So xi has to be greater than or equal to li, but also less than or equal to ui. Okay. All right. So we can satisfy this automatically if we use the following transformation. Okay. And so we have xi is equal to li plus ui minus li sine squared of yi. So just like we did in the previous example, we're going to take our original objective function and plug in this, okay? And then we're going to optimize the new function for yi. Okay? And so what's relevant here, for this yi and the previous one too, these yi can take any values. Okay? And so we can solve it truly as like a truly unconstrained optimization. Okay, any questions on this before we do an example for this one here? Is that a U? Yes, that is a U. Mm-hmm. The U stands for upper bound. Okay, let's do another example. And this example has a code associated with it as well. Okay. Okay, so we're gonna have the same objective function here. So we have f of x1, comma x2 is equal to x1 squared plus x2 squared minus 4x1 minus 4x2 plus 8. Okay. Subject to 0 is less than or equal to x1 is less than or equal to 5. Okay. So the value for x1 is constrained between 0 and 5. And the value for x2 is constrained between 0 and 3. Okay. All right, and so our starting point in this case is going to be 0, 0. Okay. And just like it always is, let's compute. Let's compute the optimal values for x1 and x2. that satisfy our constraints. Okay. And so since our constraints in this case are just upper and lower bounds, we can use our sine squared transformation here in order to get the optimal results. Okay. Okay. So let's compute the expression to plug in. Okay. So xi in this case is going to be li plus ui minus li sine squared of yi. Okay. So that's just the equation we're going to plug in. So let's compute this for both x1 and x2. Okay. Okay, so for x1, the lower bound in this case is 0 plus the upper bound in this case is 5. So we have 5 minus 0 times sine squared of y1. Okay. And so this tells us that x1 is going to be equal to 5 sine squared of y1. All right, so then applying that same equation for x2, we get the following. So x2 here is going to be 0 because that's our lower bound plus ui minus li. So the upper bound for x2 is 3 minus 0 multiplied by sine squared of y2. Okay. So this tells us that x2 is equal to 3 sine squared of y2. Okay. And so if we plug these in to our objective function, what we get is f of y1, comma y2 is equal to, okay. We had x1 squared, so that's going to be, we're going to plug in for x1. So that's going to be 5 sine squared of y1, quantity squared, okay, plus x2 squared, so that's going to be 3 sine squared of y2, quantity squared, minus 4 times x1, plus minus 4 times 5 sine squared of y1, minus 4 x2, so that's minus 4 times 3 sine squared of y2, plus 8. Okay. You can simplify this if you want, but I think what I do is I just plug this in the code just like that. Okay. All right. And so the example code for this one, the name of the file is CNLP example 4. Okay. And the name of this method is transformation. Dot. Yeah. Okay. Okay. So what's interesting about this example code here is that I actually solved the problem 2 different ways. Okay. Because if there's one method that already takes the upper and lower bounds into account, it's Monte Carlo, right? So Monte Carlo, when we do our random sampling, naturally when we do that, we have to do it with a lower bound and an upper bound, right? And so Monte Carlo will actually be able to solve this problem, no sweat, okay? And so what the code's going to do first is it's first going to solve a result with Monte Carlo, and then to kind of show that this variable transformation works, we're going to solve the exact same problem with the transformation using random walk. Okay? So Monte Carlo versus transformation with random walk. Okay? And I chose random walk on purpose because random walk is, kind of as you guys probably experienced in homework 5, random walk is probably the hardest algorithm to really kind of control. And sometimes it really just has a mind of its own. Okay. And it doesn't follow the constraints at all. And so if this variable transformation is going to work, hopefully it'll work on random walk, and then it'll work for every other method that we have. Okay. Okay. Any questions on this before we jump into the code? Okay. All right. So let's take a look at the code. I'm going to go ahead and share my screen. Okay. So this is example 4. So this is the one that's on Canvas as well. Okay. And so this is an example using the transformation method. Okay. So first thing we're going to do is we're going to solve it via Monte Carlo. Okay. And so we're sampling our random variables here. We have x1 is equal to 5 times rand. And so that's going to give us a value between 0 and 5. X2 is between 0 and 3. Okay. Completely random. We're going to evaluate our objective function. We're going to see if it's better. If it's better, that's good. And then we're going to save our results. Okay. So the first part of this code is just straight up Monte Carlo. And when you have an upper and lower bound, Monte Carlo works really well for that. Okay. But if you have a problem with an upper and lower bound, but you want to solve it with something that's more efficient than Monte Carlo, you can use this variable transformation method. Okay. Okay. So this second problem here, we're going to solve it using random walk. Okay. And so with random walk, we're going to perform our transformation. And so you can see I'm using a different objective function here. So it's t underscore objective function. Okay. And so you can see this is the objective function here. And so it's the same function as before, except instead of, just x1, I have 5 times sine squared of y1. Okay. Then 3 times sine squared of y2. Okay. Same for all of those. Okay. And so you can see we enter the random walk. And so we iterate until our step length is less than our minimum step. Okay. We do this, and then we check and see if we step in a direction, we see if it's better. And if so, then we keep it. Okay. The main thing to remember is that with random walk, at this point, there's no way really for us to constrain it. It's just going to walk randomly as it does, right? Of course, it's only going to choose directions where the objective function improves, but besides that, it's completely unconstrained. There's no limit to it at all. Okay. Okay, so it's going to do that, right? And then we finally get our result. And so once we obtain the result for y1 best and y2 best, right? We have to transform it back into x1 and x2, right? And so that's what these two variables are for. So this variable transforms the y1 variable back to x1 by taking 5 times sine squared of that variable. And then this other one takes y2 and then transforms it back to x2. Okay. All right. So this code here has 2 print statements, and so the original print statement is going to be the constrained Monte Carlo optimum. Okay. And the second print statement is the optimum from random walk, but using the transformed variable. And so if we did everything correctly, these two parts of the code should give us the same thing. Okay, let's go ahead and run it. And we come to our result here. Okay. And so from the Monte Carlo, we get a result of 2, 2, right? And so that's where the optimum is. Okay. And then for the transform random walk, we also get basically 2, 2. Okay. It may not be exactly there, but it's basically there up to 2, up to 2 decimal points, or one decimal point in this case. Okay. All right, any questions on that? Okay, all right, and so that's it for constraint optimization. And so, at the very least, the penalty function stuff, you should be using that on your final project, because there are a lot of constraints on the final project that you need to satisfy, right? You may be able to use the variable transformations in some way, but it's going to be difficult because the objective functions that we have, don't have the design variables explicitly in them. Okay, and in fact, the design variables are kind of buried within the trust codes, and so it's still possible. It's just you're going to have to be creative on using the transformations in a way. Okay. So for the final topic today, the last thing I want to talk about is a practical issue that quite a few of you have kind of been dealing with the final project over the last couple of days. Okay, and that's the issue of scaling. Okay? Specifically, the design variables. Okay. All right, so let me kind of start with kind of let's take a step back for a second, okay? And so all of the examples that we've done in class have for the most part been with kind of made up dummy variables, right? So just generic x1, x2, x, y, z, things like that, okay? One thing that we've kind of implied, or one thing that we've kind of assumed this entire time, is that all of those variables, their values are about the same order of magnitude. So all that really means is that the average values, or even the optimal values for the design variables, are all in the same ballpark, right? And so they're always either like 1, 2, 11, something like that. Okay. All right. So that's fine, and so and if you can achieve this or design an optimization problem that that can assume this, you're in pretty good shape. Okay. The reality is, a lot of times your design variables are going to have very large differences in order of magnitude. I'll give you an example. I'll give you an example from the final project, right? And so for the final project, even if we look at the simple truss, right? Let's look at two of your design variables. So let's look at the cross-sectional areas of the truss elements A, as well as the Young's modulus E. Okay. So for the cross-sectional area, okay, the cross-sectional area varies from, I think, is between 5 and 25 centimeters squared. Okay. So those are the upper and lower bounds for our design variable for that. Okay. For the Young's modulus, the range is much, much higher, right? And so the Young's modulus is, what we're saying is it varies between 500,000 pascals and 5 million pascals, right? So that's, 500 kilopascals and 5 megapascals, okay? Okay, so by itself, this is fine, right? And so you look at this as like, yeah, those are two different variables. Of course, they're going to have different ranges, right? Typical values for Young's modulus are much higher than the other ones, okay? Where this becomes an issue with optimization is that a lot of our algorithms, if you kind of notice in our algorithms, especially the ones which, you're stepping in certain directions. So I'm thinking about things like random walk, I think about things like pattern search, think about Nelder-Mead, okay? Those algorithms kind of depend on the fact that our variables all have roughly the same orders of magnitude. Okay? Okay. Let me give you an example. Okay. Let's look at something very. Let's look at random walk. Okay. Okay. I'm not even going to consider the other two design variables. So let's say we're doing just two-dimensional random walk in the A dimension and the E dimension. Okay. Okay. And so part of random walk means that you're going to have two direction variables, right? Again, R1, R2, okay? Where these R1, R2s are kind of random numbers that are going to be, based on, how much we're going to step in the E direction and the A direction, okay? Right? So R1 here, might look something like this. And so let's say that, we want to take steps in the A direction that's between -5 and 5. So we have -5 plus 10 times rand. Okay. Or excuse me, -5 plus 5 times rand. Okay. So it is 10. I'm sorry. Tripping. The upper bound minus lower bound. Lower bound is -5, upper bound is 5. Okay. And then for E, we may make modifications, maybe let's say -50,000 to 50,000. Okay. So this is going to be modify A between -5 and 5 centimeters square. And this right here is going to modify E between -50,000 Pascal and 50,000 Pascal. Okay. Okay. So we can compute these things. It's okay, right? So it's going to be random numbers between -5 and 5 and -50,000 and 50,000. Okay. All right. So the next part of the code, right, or the next part of the algorithm of random walk is we have to compute the magnitude of this direction, right? Okay. So this is going to be square root of R1 squared plus R2 squared. Okay. Right. And if you remember the reason we do this is to mostly check for bias in our direction. All right. So here we start to see the problems already, right? So if we compare the relative magnitudes of R1 and R2 here, right? R1 we know goes between -5 and 5, right? So R1 is naturally going to be usually going to be a much smaller number than R2, right? There may be random instances where R2 is smaller because of just R and G, but for the most part, R1 is going to be much, much smaller than R2, right? And so when you have such a very big difference in quantities here, and you're essentially adding them together, it's going to be as if one of these does not exist, right? And so the only term that's going to dominate this expression is going to be R2, just because it's orders and orders of magnitude larger than R1, okay? And so when we check for bias, essentially we're only going to be checking for bias in the R2 direction because R1 is simply not going to exist, okay? Okay. All right, so how can we fix this, right? And so the idea here is that instead of computing the raw values like this, we want to modify this or scale this in a way such that R1 and R2 are roughly the same magnitude, so they both kind of contribute equally to the R magnitude. Okay? And so the answer to this is actually in the question itself, right? And so the answer is to basically scale these, okay? And so instead of computing that quantity like that, okay, you can think of computing something like this, right? And so you would have R1 divided by, and it doesn't have to be anything specific, right? We just want to make sure that R1 and R2 get roughly on the same page, roughly the same magnitude. Okay. So maybe do R1 divided by, let's do the upper limit of R1. So R1 upper, okay, squared. Remember, R1 upper here is 5 centimeters square, right? So that's the upper limit on the variation that we're going to do. Okay. Plus R2 divided by R2 upper. Okay. With R2 upper right here is the upper limit on the variation in the Young's modulus. So this would be 50,000 Pascal. Okay. And quantity squared. So by doing these scalings, right? So then that quantity, that first quantity in parentheses there, and the second quantity in parentheses there, because we're scaling based on the relative magnitudes of these two quantities, when you add them together, they're going to be roughly the same orders of magnitude. Okay. And that's generally what you want. Whenever you have expressions that are adding together terms with different orders of magnitude, you usually want to scale it in a way such that they're all roughly the same. Okay. So that's kind of the summary of kind of scaling and kind of why you do it in this scenario. Okay. Another way that you can look at this is in terms of the units, right? And so whenever you're adding, and this goes beyond optimization for any engineer, right? Whenever you're adding two quantities together in an expression, kind of the assumption or kind of the implicit thing that you're assuming is that those two things have the same units, right? Because it doesn't make sense to add together a Young's modulus and a length together, right? Because that's nonsense. That gives you nothing, right? And so, in optimization, that line gets blurred a little bit because, we're handling things kind of, almost purely on the mathematical side, but the same rules, the same kind of conventions for these units and scalings and things, they all still apply here. Okay. All right. So I want to talk about this kind of specifically today because I know a few of you are doing, random walk, coordinate search, pattern search, for the final project. And you may have to apply, and not may, you will have to apply scaling to those methods in order to get them to work properly, for the truss structure that we have. Okay. Okay. Any questions on this? Okay. So you can see scaling on multiple different levels too. Okay. In fact, the project already applies some principles of scaling in its objective function, right? And actually, I applied scaling twice here, right? And so if you look at the formula for the total cost, okay, of a truss structure, and this is for the simple truss, what I told you was that the total cost is equal to the total volume of the truss structure plus 4 times 10 to the minus 8 times the Young's modulus squared. Okay. a couple of you have asked me, you know, what is this 4 times 10 to the minus 8? So what is this doing here? So this constant here is providing some scaling. Okay. Because remember, we just talked about the Young's modulus is often a very, very high number relative to all the other parameters in the problem, right? And so if we eliminated this, and so if we just said that total cost was equal to the volume of the total volume plus the E squared, right? The only term that's going to dominate in that expression is E squared, because E is so big. By itself, E is already really big, but when you square it, it becomes even bigger, right? It's going to be as if the total volume is not going to matter at all, because E is going to dominate everything. Okay, and oftentimes you don't want that, right? And so oftentimes, you know, when you're comparing multiple things together and you're adding it together, you want to scale it so that you know it's more reasonable. Okay. All right. And actually, on the topic of units, you know, technically speaking, you know, we should be applying a scaling parameter here as well. Okay. Because remember, what we're computing here is cost, right? So cost has units of dollars or money, right? So volume is not a cost, right? And so technically we need a factor there to convert volume to cost. But you know, for simplicity's sake, I assume that coefficient was just 1, right? But technically speaking, you know, in order to convert stuff, you need a scaling constant. So you can add something there if you want to your own code, but you know, it's not strictly required. Okay. The other place where scaling is applied is in the objective function itself, and this one's a little bit more explicit. Right, and so the objective function that I gave you for the simple truss looks like the following, right? And so what we're saying is that we're optimizing 2 quantities in the final project. We're optimizing the total cost of construction as well as the total deformation of the structure as well. Okay. And so in order to make sure that these 2 things are able to be added together, we scale the cost by some reference cost, and we scale the deformation by some reference deformation as well. Okay. And so we square it and then we square root it, then this allows us to compute the objective cost. Okay. All right, so scaling is very important, and especially when you're working with practical problems and your design variables all have different units. Oftentimes, you're going to have to apply some kind of scaling in order to make sure that everything kind of works together and the algorithms kind of do what they need to do. Okay, and so if you're having trouble in the final project, if you're either find that your Young's module is not changing at all, or if your random walk is not doing anything, the issue is probably most likely due to scaling. Okay. All right. Any questions on this? Okay. All right. So that's all we got time for today. If you haven't had a chance to pick up your exam, I have them here today as well. You can come pick it up in the front. If not, I'll bring them to class next week as well. Okay. So the plan next week, like I mentioned on Tuesday, we're going to go over just a few more practical details with optimization. We're going to go over how to use the built-in methods. Okay. The built-in methods are nice because they kind of give you a nice test bed, so they can give you kind of an example of what an optimal solution looks like. Okay, you can do that for the big truss and the small truss. And then next Thursday, we're just going to have project workshop. Okay. All right, so thank you guys for coming today. We're very quickly approaching the end of the semester. Hope you guys have a good rest of your weekend. If you have questions on the project, definitely don't be afraid to reach out. Let me know. Come to office hours, send me an email. I'm always happy to look at code if you want me to look at it, right? And I will see you guys next week. Oh, that's 4:10 minutes later.
And you sure didn't get us last time? Actually, do you think give us the midterm and not the final project, really?
The midterm project?
The final project, but,
Sure, yeah.
you mentioned that we work in pairs, and the senior design project people. The only thing that, me and Kevin,
Mhm.
another classroom.
Hang on, let me stop this.